In the previous video, I introduced you to the idea of torque. The torque is a measure of the effectiveness of a force in changing an object's rotational motion. In this video, we ask what determines the response of an object to a torque. Or in other words, suppose I apply the same torque to two different objects. If I apply the same torque to two different objects, will those objects respond in the same way, or will they respond differently? In this video, we're going to be doing a couple of demonstrations to address this question. I'm going to be doing these demonstrations using objects which are probably available to you within your own environment. So once I've described to you what these objects are, I'd encourage you to pause the video and then go and try to collect some versions of these objects for yourself. So here's what I have. I have a bunch of stackable spoons. So I have five identical spoons here, which you can see fit into a stack. I also have here a couple of identical mechanical pencils. On this mechanical pencil right here, I have taped a stack of quarters, and I have taped the stack of quarters closer to the eraser side of the pencil. And on this pencil over here, I have taped a stack of 8 quarters, and I have taped the quarters closer to the tip side of the pencil. So I would encourage you, if you have this stuff available to you, go and grab a bunch of spoons, and then go and grab a couple of pencils and see if you can tape identical stacks of coins to different locations on the two pencils, and then we can do the experiment together. So let's get started. So I'm going to just take one spoon by itself here, and I'm going to shake the spoon back and forth like so. As I shake the spoon back and forth, my fingers are constantly exerting torques on the spoon. As you can see, the effects of those torques that my finger exerts on the spoon are to constantly change the rotational motion of the spoon, right? I go from having the spoon rotate counterclockwise to having the spoon rotate clockwise, to having the spoon rotate counterclockwise, to having the spoon rotate clockwise, and so forth. Okay? And you can see, or better yet, tell by your own experiment, that when I'm doing this with just one spoon, it's fairly easy to get that rotational motion to repeatedly go back and forth from clockwise to counterclockwise to clockwise to counterclockwise, and so forth. Now, let's try the experiment with a stack of multiple spoons. Here I have 4 spoons, and hopefully you have a stack of spoons as well. And now I'm going to try the same thing with the multiple spoons. And I can feel, and I hope you can feel as well, that with the stack of multiple spoons, it's much more difficult to get the rotational motion of the spoons to keep changing from counterclockwise to clockwise, from counterclockwise to clockwise, and so forth. So to sum up, it is fairly easy to keep changing the rotational motion of the one spoon back and forth. It is much more difficult to keep changing the rotational motion of the stack of 4 spoons back and forth. This pair of experiments is straightforward to understand. The stack of spoons has more mass than a single spoon, and a greater mass will be more resistant to changes in its motion. In particular, a greater mass will tend to be more resistant to changes in its rotational motion. So the experiment with the spoons tells us that an object with greater mass will have more resistance to change in its rotational motion. Now let's ask a different question. Is it possible for 2 objects with the same mass to have different resistances to change in their rotational motion? To answer this question, we're going to pull out the pencils that have the stacks of coins taped in different locations. So this pencil here has a stack of 8 quarters taped onto it, close to the eraser end of the pencil. And this pencil here has a stack of 8 quarters taped closer to the tip end of the pencil. Notice that each of these objects has the same mass. Here I have a pencil with 8/4 taped to it. Here I have an identical pencil with 8/4 taped to it. So this object and this object have identical masses. They only differ in where the stack of quarters is taped onto the pencil. So now we're going to take that same experiment that we did with the spoons and do it with the pencils. First, I'm going to take this pencil that has the stack of quarters taped close to the eraser end. And if you're doing this on your own, I found that it's easier to rest the eraser on my middle finger and then use my thumb and first finger to grab the eraser end of the pencil. And then I can shake the pencil back and forth, and that was actually not so hard. Now I try the same experiment with the other pencils where the quarters are attached further from the center of rotation at my fingers. When I try that same experiment with the quarters attached further from my fingers, I can feel a much greater resistance to changes in the rotational motion. When I do the experiment with the quarters attached further from my fingers, it is much more difficult to keep changing the rotation from counterclockwise to clockwise to counterclockwise to clockwise and so forth. So to sum up here, I have two objects with identical masses, but when the distribution of the mass is closer to the center of rotation, it is much easier to change the rotational motion. When the distribution of the mass is further from the center of rotation, it is much more difficult to change the rotational motion. So to come back to this question, it is in fact possible for two objects with the same mass to have different resistances to change in the rotational motion. In other words, we have seen that when we have a distribution of mass where the mass is located further from the center of rotation, that object will have more resistance to change in rotational motion. So to sum up, the experiments we have done in this video have shown that two different things determine an object's resistance to change in its rotational motion. The mass of the object partially determines the resistance of the object to change in its rotational motion, but the distribution of mass within the object also determines the resistance of the object to change in the rotational motion. In the next video, I will introduce you to a single quantity which describes the resistance of an object to change in its rotational motion. That single quantity will take into account both the mass of the object and the distribution of mass within the object.